Inverses and Symmetry 12.1b. We've got one previous video for this chapter that's linked in the description. We can determine whether the graph of a relation is symmetric with respect to the line y equals x. And interchanging first and second coordinates of each ordered pair of a relation has the effect of interchanging the x-axis and the y-axis. Interchanging the x and y-axis has the effect of reflecting the graph of those points across the diagonal line whose equation is y equals x. So here's an example. We have a diagonal line y equals x, and we can see that this point right here is a 9 and a 15 for x and y, and it's reflected across as a 15 and 9, and it's the inverse of this point. See? So the graphs of a relation and its inverse are always reflections of each other across the line y equals x. A simple transformation of the equation corresponds to a simple transformation of the graph. If interchanging x and y leaves the equation unchanged, then the graph will also remain unchanged. So we could have x times y equals 4 or y times x equals 4. The equation is unchanged, so that graph would be unchanged. We say that the graph is symmetric with respect to the line x equals y. Now here's some examples of some graphs and their inverses. Here's our line, y equals x, and the blue one is reflected across as the green one, see? And it's symmetric, isn't it? And these two are symmetric as it's reflected across. And take a look at these. Look at how the green one reflected across as the blue one. See that? A relation may be its own inverse if, when the relation is reflected across the line y equals x, the image is unchanged. And this type of relation is symmetric with respect to the line y equals x. Now see, this one said it was respect to the line x equals y. See? And we can test the relation 3x plus 3y equals 9 for symmetry with respect to the line y equals x by interchanging x and y in the equation. We get 3y plus 3x equals 9, which is equivalent to the original equation. So the graph is symmetric with respect to the line y equals x. And we can test the relation of 4x minus 4y equals 8 for symmetry with respect to the line y equals x. When we interchange x and y in the equation, we get 4y minus 4x equals 8. Well, this isn't equivalent to the original equation, so the graph is not symmetric to y equals x. Look at it this way. If we have a 1 for x and a 2 for y, and we switch their places, well, the commutative property says it doesn't matter what order the addends are in. Once we get the product, it's still going to equal 9. But if x is a 3 and y is a 1, and we do it this way and they interchange, we're going to go from 12 minus 4 equals 8 to 4 minus 12 equals a negative 8 in order for this equation to be true. And these equations are not equivalent, so the graph is not symmetric to y equals x. All right? So we'd end up with a graph that's not symmetric. Our next video is 12.1c, and we're going to talk about inverses of functions, and I have another theorem for you. There's going to be a link to that previous video for chapter 12, and there's going to be a link to 3.1b where we talked about relations back in chapter 3. And there's going to be a link to the Algebra 2 playlist, so you can go to that quickly if you want to. I'm going to add this to the Algebra 2 playlist, and I want to remind you that you can go to YouTube fan funding, patreon.com/JoAnn School, or even PayPal now. Just go to my homepage, or you can even check the links in this description to go there and help support me and my cause of trying to get math all around the world and trying to help everybody. And I'd appreciate the support. So I'll see you next video, and let's talk about some inverses of functions. Bye.